Hi, this is Chris Brown, and this is lecture 2.19 in axiomatic design and manufacturing processes. And so for the next few minutes, I'm going to be talking about energy and following that in the manufacturing process. So why energy? Well, work is required to add value, and we need the energy in order to do the work, to change something in order to add the value, like in mechanical parts, shape, surface, and mechanical properties. And we see big changes in the standard of living of people when we learn how to harness energy. So we have this kind of energy work theme that we can use. So we need to do work on materials to produce shapes and properties. And so let's see where that work is being done and what part of the work is really adding value. So what adds value to mechanical parts? So geometric accuracy, being able to hold tighter tolerances, so trueness and precision on a relatively large scale, I suppose, and then the surface finish on a relatively small scale. And so this would be the texture, the roughness, lay, and then the strength. So other properties, optical, electrical, chemical, biological, magnetic, those can be important as well too. But energy. So where does the energy come from? Now we talked a little bit about Emily de Châtelet in an earlier lecture, and she was looking at this experiment that was done, I think in the Netherlands, by Segrave Sand, and he was dropping balls into clay from different heights, and noticed that balls with twice the speed would leave an indentation 4 times as deep. So somehow he comes up with the 1/2 mv squared, or starts on the, it's Emily de Châtelet that comes up with the 1/2 mv squared, but he's looking at this impact. Anyway, so we still deal with impacts in manufacturing. Here's a surface that was grit blasted, and so we can see here the impact craters and dissipating the energy from the incoming grit. And here's a number of them, and we can see after 1, 5, and 10 times under the grit blaster what the surfaces looked like. And here at one time we can see the individual impacts. This material is the softest, and this one is the hardest. So we can see how, with the same energy, the impact craters are relatively smaller here. So anyway, it's still sort of a valid thing. And let's just take a look at machining here too. So Count Rumford, interestingly enough, he's born in Massachusetts, ends up on the British side in the American Revolution, so leaves to go to England. And then he ends up in Germany boring out cannons. And so he notices that there's a lot of heat coming out, so he sets up a little experiment. And here's a depiction of it. You had some horses walking around, and then you had something boring out the cannon. But what he did was he put the whole thing into a big barrel of water, and eventually the water began to boil. So he was able to show that, or he was surmising that heat was not in the cannon to begin with, that it was somehow transferred to the cannon by the work that was being done to machine it. So work energy. So if we take an integral of the force times the velocity over time, so we can transpose this, and we get the familiar f dot dx, and then f dot dv dt can go into work is equal to 1/2 mv squared, or the difference in the velocity squared. I want to note here too the work of Steve Malkin, who has done a lot on grinding and the thermal aspects of grinding. Steve passed away recently. He was at UMass Amherst for a number of years, and he's written a book with Gao, and here's the second edition is with Gao. And there's a paper that I recommend reading on the thermal aspects of grinding that was delivered in CERT just a few years ago. So one of the things that Steve did was he talked about energy partition in grinding, and that's particularly interesting, and I think it's a good example of how to do this stuff. So the grinding zone is modeled as a heat source which moves along the surface, and the grinding energy, or the work that goes into the grind, is converted into heat, and then transferred to the workpiece through the contact zone. So the kind of energy partition, how much goes into the workpiece, how much goes into the chip or the fluid, is important in understanding how well the grinding process is going and what impact it may have on the properties of the workpiece. So he introduces this sort of energy partition along a number of years ago, back in I think late 1970s. So this is the fraction of the total grinding energy that's transported into the workpiece as heat in the grinding zone. And naturally this depends on the type of grinding, the wheel, the workpiece, and the operating conditions. So we have a depiction of this here. So here's a grinding wheel that's spinning around, and here's a workpiece that's spinning around, and you can see here's the part that's being removed, and this is the contact zone right here, and so here's the heat going into the workpiece in the grinding zone. And so we could take a look at a little element like this, and so it's a moving heat source kind of problem. All right, so the energy partition, and it's derived from a grinding model and can consider fractions for the chip formation, for the plowing, and for the sliding energy, and then what's conducted into the workpiece. And so in shallow grinding with conventional abrasive wheels, the energy going into the workpiece is about 60 to 85% of the total energy. So let's zoom in and see what this looks like. Here's a little chip forming, and it appears to have a little shear angle there, and it's the grinding wheel is going this way, or the workpiece is going that way, and so what we're seeing here is a negative rake angle, and a lot of work being done to create a very small chip relatively. Of course, in grinding we have a number of sort of cutting tools available, and so we're not just waiting for one. So the abrasive grain looks something like this, and so here's the rake face on the grain. Here's the chip flowing up. There's a shear angle, highly depressed because this is a negative angle, negative rake angle, and here's the wear flat. And this is just rubbing against the surface, and so that's creating heat there. And in grinding, we don't just remove a chip, we also move material around on the surface. For example, here it gets pushed aside into these little ridges with a groove down the middle. So what are the lowest process variables, the most detailed process variables in an abrasive process? Well, we've got the speed, usually the wheel, but it could also be the workpiece. Lubrication, so you get coolant, flow rate, distribution, and the application. Now, John Webster does a lot of work with the coolant. Feed, workpiece into the wheel. That tells me how much I want to take off, or how much I can take off in every grinding pass. The wheel geometry is important. The roughness of the wheel, grain size, grain geometry, grain spacing, because we have to carry the chips out and coolant in. Workpiece material, of course, is important. Wheel hardness, fixturing, size of the wheel, abrasive fixturing. So that's sort of a different kind of process. The power, the depth of cut, abrasive material. All right, that was as far as I want to go. All right, so the kind of material they're using. So once again, you can see we have a lot of PVs, just like we did in machining, probably even more. So sort of going backwards through this, we go, well, do we have FR as it goes up to? And once again, we don't really. So we have redundant kind of design possibilities, because we could say, well, here's what we think are the most interesting abrasive processes in this case, and then it turns out that maybe somebody's too far south or something else, and so they can't get water that won't anyway. All right, so let's take a look at something else here. So here is a cutting force as a function of feed rate, and we notice that there is at zero force there is, or zero feed, there's zero force. So the and we also notice that up in this region there's a fairly linear relationship between the force and the feed, and that I noted too earlier in an earlier lecture. If we extrapolate this, it comes back to a positive intercept on the force axis, and so we have this sort of positive force displacement, and actually the axis should be out here at 0, but you get the picture. Anyway, so at about 200, or if we extrapolate back, we've got about 200 newtons of cutting force in this extrapolation, and when we know that if the feed is 0, that there shouldn't be any. So there's sort of 200 newtons of extra force here. And what is that doing? Well, that, it turns out, seems to be equal to, and some unpublished work we did, equal to the amount of force that you would need to put the amount of heat in the workpiece that we're seeing. So this is the cutting forces in the direction of motion, so that's work. And so if I take the heat that's in the workpiece and compare it with this force and go through the calculations like we've just seen, it appears that this is about equal to the heat that's left in the workpiece. So most of the energy in machining goes into creating the chip, which has no value to the customer. In grinding, most of it goes into the workpiece, where it can create unwanted surface properties. If you get the stuff too hot, and then cool it off the right way, you can end up with large residual stresses. So, how much, in these cases, how could we get more of the energy into creating value and less into doing sort of chip removal and unwanted work? And that's one of the challenges that's going to face, that is facing manufacturing engineers. Great, thank you very much for your attention.